Hello guys, welcome back to another video. I'm recording this at currently 1:38 a.m. so it's very late, so I have to talk really quietly. Anyways, right now I didn't cover this formula in last video. I thought it would be pretty trivial because, well, efficiency just measures how well your output is divided by how well your input is, and you just multiply this by 100 if you want the percent efficiency. So for example, if we have a motor takes in 200 joules of electrical energy, and it does 150 joules of useful work lifting the box. So the motor's efficiency, you would just take the output divided by the input. It doesn't matter what units they are, because even if I put the units here, one unit is in the denominator, right? You have 150 joules in the numerator and one in the denominator, right? So they're just going to cancel out, and we get all of this multiplied by 100 to make. So the motor's efficiency is 75%, meaning that 75% of the energy that you put in is actually used for useful work. The other 50 joules, or you can think about it as the other 25% that is lost, right? The 50 joules that is lost, or the other 25% that is lost as heat, all right? Generally, when you're talking about efficiency in like real life processes in the real world, they're usually never going to be 100% efficient because a lot of it is lost as heat. The thing is that I do not know how to animate. I'm sorry, guys. But
in a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
There's actually another vocabulary term, and it's called the medium of the wave. And the medium of the wave is just what the wave is traveling through. So for example, in this wave right over here, what is the wave traveling through? Well, it's traveling through all these coils. So these coils would be called the medium of the wave. For example, sound waves, they got to travel through the air. So the air would be the medium. Water waves, well, they have to travel through water, right? So the medium for water waves would just be water itself. A lot of times, the medium of a wave is, just the thing itself, like water waves, the medium is just water. But, I mean, that's not always the case, but, it's pretty nice to look out for these things. You just have to ask yourself, what is the wave traveling through? Now, if I look at this transverse wave, I just want you to take a look at just this one coil. All right, just take a look at this one coil here. All right, if you look at this animation, notice how the coil isn't actually moving forward, right? It's the wave that's moving forward, but the coils are just moving up and down, right? These coils, they're just moving up and down. They're not actually moving forwards. So it's like the optical illusion. The wave is moving forward, but kind of the direction that the medium sort of goes is just going to be perpendicular to that. Whoever made this interactive physics simulation, well, this guy's going to heaven, because this is absolutely amazing. Like, so you can see how amplitude, right? Normally, maybe in your Algebra 2 class, you might have heard of amplitude as being like, the distance from the middle of the wave to essentially one of the peaks of the wave. And these peaks right over here, we call crests. So this top peak, this top peak, this top peak, they would be called crests. Meanwhile, the bottom of the wave, all the way at this bottom right over here, they're called troughs, okay? Now, if I decrease my amplitude, you can see that the distance from the middle to the top is shorter than if I increase the amplitude. Now, how does that look like from a longitudinal wave's perspective? So this is a transverse wave. This is probably what you've encountered before, but how does the amplitude look like in the context of longitudinal waves? Now, as you can see here, you have this amplitude here. And I just want you to take a look at a specific kind of line of the longitudinal wave. All right, so watch this. Just focus on this one line, all right? Just focus on this one line. So it goes back, then it goes back again, okay? And then it goes back again. So you can see that during that entire sort of cycle, the line traveled from here all the way to back there, then back here. So you can think about the amplitude as just being half of the total distance that was moved by the line, right? The line moved all the way here to the back here. And then the amplitude essentially measures half of that distance. And just by the name of frequency, well, the wave just goes up and down more frequent. That's basically what it means. And you can see it for both waves as well, right? You can see that for my longitudinal wave, there's like these sections where it's like really clumped. There's like a lot of waves in this one area. if I increase the frequency, well, now there's more of these clumped spaces for the waves. And you can see the same thing for the transverse wave. So the higher the frequency, the more the wave just goes up and down, or the more the waves just are clumped together through a specific time interval. So let's watch this. And yeah, this is a really, really cool simulation. I highly suggest y'all to check this out for yourself because this is very, very cool. Okay. So this is just going to be a little review of what we learned. So for kind of a given sort of top of the wave and a given bottom of the wave, that's a crest and trough respectively. And you're also going to be introduced to the idea of wavelength. And wavelength just measures the distance between sort of consecutive points, the same sort of consecutive points on this sort of wave, right? So notice how this is like the same distance here, right? Now, the thing about wavelengths is that, well, it has to be moving in the same direction. Now, what do I mean by that? This point right over here and this point right over here would not be considered a wavelength. That is not the wavelength distance. And you might be saying, what? How? These are the same height, so they have to be the wavelength. Now, the thing is, you also have to take into account direction. Notice how this dot right over here is going down. And this dot right over here, this is pointing upwards. You want the wavelength is just when the two dots right over here, they're the same height, but they also have to be pointing in the same direction. So that is what I mean by the 2 points got to be consecutively corresponding. They got to point in the same direction and they got to be the same height. Finally, remember amplitude, right? Just the distance from middle to all the way to the top. You also have frequency. Frequency, we talked about this before, but it's essentially how much does the wave do this? All right, that's basically frequency. And the way to find that, well, frequency has the units cycles per second. All right, how many cycles occur for every second that passes? All right, and another way to say this is using the unit hertz. All right, that's actually another, that's basically hertz is the unit for basically the frequency. So for example, if I say that my frequency of a wave is, let's say, 5 hertz, all that means is that every 1 second that passes, well, my wave is going to be cycling up and down sort of 5 cycles. That's all that means. The period of a wave, however, these are very, very common concepts to get confused. You'll notice here how period, and you'll see period is symbolized by t. You're just going to take 1 divided by your frequency. All right. So for example, if I wanted to find the period of my wave, which is originally 5 hertz, if I want to find the period of it, I would just take 1 and I would just divide it by my frequency, 1 over 5 hertz. Now the period is going to be measured in seconds, second per cycle, right? Because if frequency is measured in cycles for every 1 second, well, if I reverse this, right, if I sort of flip this around, then period is going to measure seconds per cycle. So all period does is it tells you, well, how many seconds does it take for 1 cycle to occur? And you can see that when I do this calculation, 1/5, that's approximately, that's just going to be 0.2 seconds per cycle. All right, these two answers make sense. If my wave is going 5 cycles every 1 second, well then 1 cycle would just take 0.2 seconds. Sound waves are a specific type of longitudinal wave. And for sound waves, you can see how the sound from this megaphone thingy is pumping out this way. And you can see how the waves are traveling in the same direction as, the direction at which it's pumping out. But the thing is, sound waves, well, they kind of go 360 direction, right? You can see that it goes from every direction. Now, let's take a look at how frequency and amplitude affect the sound. Now, when I play the audio in this video, it kind of gets messed up. So I recommend y'all to try this yourself. But just to know that when you increase the amplitude of the sound waves, what that essentially does is that increases the loudness, right? Or the volume of what you're hearing. So it's going to be louder if you increase the amplitude and quieter if you decrease the amplitude, of course. And for the frequency, well, in music, you might have heard of like pitch, like, like an opera person, like singing in a very high pitch, right? If you increase the frequency, that affects the pitch. All right. And if you decrease, that decreases the pitch. All right. So amplitude, this is for loudness, and frequency, this is for pitch. this is something called the Doppler effect. Basically, this is why, like, if a train passes you, like as you see in the video, it seems to have like a very high pitch, but then when it passes you, then it becomes like a very low pitch or a very low frequency. Why is that? Well, take a look at this diagram. As the source sort of moves in the direction of the sound waves, it sort of or bunches up, I guess you can say, right? You can see all of this bunches up, and therefore you're going to experience a very high frequency at first. But then as the source moves away from you, you can see as the source moves away from you, the sound waves don't bunch up as much, right? And therefore, that's going to cause a very low frequency, right? You can see the back observer here. This is a very low frequency compared to all of these sound waves are bunched up together, all right? And that's like the amazing thing about it. The actual sound itself, like the actual source of the sound, isn't actually like changing. That's the important thing to know. Like the actual source of sound is the same frequency. It's, the same amplitude in this case, but it's just how you perceive it, right? Even though the source stays the same, how you perceive the frequency changes depending on where you are, all right? And that's important to know. So once again, these are just some extra things you can like check out. It's pretty cool. You can see that all these sound waves gather up in the front, high frequency, but then as the source moves away, you're gonna perceive a lower frequency, right? This is the Doppler effect formula. This is, I know it's a lot, but our observed frequency is going to be equal to the actual frequency of our source multiplied by the velocity of my sound wave, and then it's going to be either plus or minus the velocity of our observer divided by the velocity of my sound wave once again, minus plus the velocity of the source. All right, let's just explain what's happening here. If the source and the observer are moving towards each other, well, notice how this observer is now going to get a positive sign, which you can see here. And then my source is going to get a negative sign, which you're going to see here. So basically, if the source and the observer are moving towards each other, just use these top symbols. All right, you just use the positive symbol up top and the negative symbol up here, right? Just use the top symbols. Meanwhile, if the observer and source are going away, well, you would use these bottom symbols, right? The yellow matches with the yellow. So the observer is going to get this negative sign, and then the source is going to get this positive sign. Of course, you can like mix and match these scenarios, quote unquote. Like, let's say if we have a source moving this way, and let's say my observer is also moving this way. Well, notice how the source is moving away from the observer is moving away from my source, right? So it would have a negative sign here. So the observer is moving away from the source, so it's going to have a negative sign, while my source is moving towards the observer, so it's going to have a negative sign like this, right? So in this case, it would be a little more difficult to tell which sign to use, like the plus or minus sign, but, I feel like this diagram is really good because as long as you draw this diagram and you know the formula, well, then you know what scenarios to use the symbols on. You have this police car, which is my source, and let's say this is my observer, and let's say that, well, the police car is moving at 25 meters per second, and the observer is moving towards the police car at 5 meters per second. So because they're moving towards each other, well then, if you're moving towards each other, I know I got to use this first scenario, or, the top formula, right? The top symbols. And the siren has a frequency of this, and the speed of sound is this. What frequency does the observer hear? All right. So now we can just use the formula. So my observed frequency is going to be equal to the actual frequency, which in this case is 700 hertz, right? Right now here. And now we're just going to multiply everything. So the velocity of my sound wave is 343 plus the velocity of my observer, which in this case is 5 meters per second. I'm not writing meters per second down here because think about it. I have a velocity up top, and velocity isn't measured in meters per second. And I also have velocity on the bottom, which is also meters per second. So just notice how meters per second and meters per second just cancel out. So at the end of the day, I'm just not going to write it out here, right? Because you're just going to cancel out. But you also notice how my frequency, remember what frequency is measured in? It's measured in hertz, or 1 over seconds. So notice how if all of the units here cancel out, you're just going to be measuring with hertz as the observed frequency, which makes sense because frequency is measured in hertz. So once again, units are really important. Anyways, we're going to divide this by our velocity of the sound wave, and then it's going to be, remember, minus sign because it's going towards, right? You have this minus sign here and the positive sign here. So remember, minus sign in the denominator if it's going towards, right? If it's going towards, minus sign. So we are going to subtract this by the velocity of the source. And then now this is just putting into the calculator, and now 766 hertz as my answer, okay? For those of you who are worried about rounding during the Regents physics, let me just show you something that will make you very happy. When you're expressing numerical answers, and this is the literal physics rating guide, so grading for everything, It says, do not penalize students for not using significant figures. Allow credit even if a student has rounding errors or truncation errors. If this is the correct answer, then 3.25, 3.2, 3.3, and 3 would all receive credit. And for scientific notation, you can write it in 3 ways. All right, that's just a bless right there. Like, whoever did that, I'm going to heaven. Say if we have a vacuum, and let's say that in this vacuum right over here, I have some light. All right, now a vacuum is just a space where there's really like not much particles. Like, think about the space around you right now. If you look around you, there's air molecules everywhere. So this is you, and around you, there's air molecules everywhere, right? But in a vacuum, there's literally like almost 0 air particles sort of blocking your way. All right. Now let's say in this vacuum, I have some light, and I put this light, inside the vacuum, and I track how fast it moves. All right. Now it turns out that light in a vacuum moves at a constant speed, which is the speed of light, and it's about 3.00 times 10 to the 6 meters per second. And the speed of light is going to be equal to the frequency multiplied by the wavelength, which you use this sort of lambda symbol, this upside down Y symbol, to represent that. And it doesn't even matter what type of light it is. So the speed of light is this value, and this doesn't depend on the type of light, meaning that you can have any sort of light inside my vacuum and it's still going to travel at the same speed. All right, so speaking of the type of lights, well, you have something known as the electromagnetic spectrum, and this basically just shows sort of all the lights, So first off, you have radio waves, and you can see how radio waves, well, they have a very low frequency. All right. Now, what does it mean when you have a low frequency? Remember, frequency is just how many times the wave just does this in a single second. All right, how many times does it just go up and down, in a single second? All right, so this is like a wave that's not very frequent, and this right over here is an example of a wave that has a high frequency. Notice how when the wave becomes more frequent, so when the frequency increases, notice how my wavelength decreases. Notice how the wavelength, the distance between, 2 consecutive corresponding points, notice how that decreases. Meanwhile, take a look at this first wave. Because my frequency is so low in this wave, well, then the wavelength becomes super duper long. Right? The wavelength becomes super duper long. So this is something known as just an inversely proportional relationship, meaning that as one thing goes up, the other thing goes down. Okay. So there we go. Now you can see how X-rays, you have gamma rays. These are super high energy waves. They have very high frequency. Okay. And you also have, Wi-Fi, of course, here, but then you also have visible light. So it turns out that out of all the light here, only like a small portion of that scale or the spectrum we can actually see. You can see that red light has the lowest frequency. Red light has lowest frequency, while violet light has the highest frequency. All right, so that is also another important detail. All right, now this is like a very powerful tool. It's basically saying that no matter what frequency of light I'm dealing with, no matter what wavelength of light that I'm dealing with, I'm still going to get the same speed of light in a vacuum. All right, and this is actually in your physics reference table, thank God. And this is just saying that the velocity of our light is going to be equal to the frequency multiplied by the wavelength. The reason why it says the velocity of light is because, well, imagine if this wasn't a vacuum. Imagine if this was like air, for example. Imagine instead of the light moving in a vacuum, the light is moving in air. So instead of the speed of light, you would just say the velocity of light, right? Because obviously, you would just say the velocity of light here. Because, obviously, if your light isn't moving in a vacuum, it's going to travel at a different speed, right? The speed of light depends on what material you're sort of traveling through, or sort of the medium of which the light is traveling through. If the light is traveling through like air, that's going to travel at a different speed than a light that's traveling through, let's say, water, for example. Water. Back to the electromagnetic spectrum. Radio waves, who even uses a radio these days? These are so low energy, right? these are so low energy. But if we compare them to X-rays and gamma rays and ultraviolet waves, I mean, you usually associate these waves as being very powerful, or they have like a lot of energy, right? These waves have a lot of energy. So you can see that on a scale. If you have a very low frequency, you'll have a low energy. But if you have a very high frequency, you'll have a high energy. Is there any way to relate? Is there any way to relate the frequency of a wave to the energy of the wave? Is there any way to do this? And the answer is yes. This is a constant in your reference table. I don't actually know if they. Oh yes, they do have it. So it basically says that the energy is equal to this constant right over here, which is Planck's constant, and I hope they give it up top. Yes, Planck's constant is up here. This is 6.63 times 10 to the negative 34 joules per second, and so this is going to be equal to Planck's constant multiplied by the frequency, and that's just going to give you the energy of light. All right, the energy of that light. Okay, now, I mean, if your teacher is like really devious, like what they can do is they can give you the velocity of light, they can give you the wavelength of light, and then they ask you to find the energy of that light. So what you would do is from this top formula, you're given the velocity and the wavelength, so then you would solve for frequency, and then once you solve for frequency, then you can plug into the formula. So at most these problems might be like a couple of steps, maybe even if like the teacher gives you like the period, then you can solve for the frequency, and then then you can actually get the energy of the photon. But the point is that these type of problems, you're literally just plug and chug from the reference guide. So now light has a wave particle duality, meaning that sometimes it sort of behaves as a wave, but sometimes it also behaves as a particle. And a photon is basically a packet of light, and it sort of follows this wave particle duality. And this is why this says the energy of a photon. Once again, I have another wave simulation for you guys from O Physics, and this basically shows constructive and destructive interference. So we have two waves, and they're like meeting each other, right? They can interfere with each other. The waves can interfere, and it can either be constructive or destructive. Now, let's take a look at constructive interference. All right, so this is constructive interference. I'm just run this. You can see it creates a bigger wave. So when two waves are sort of, I guess you can say, along the same sort of, side, well, it creates this sort of bigger wave. If I actually zoom in, you can see it creates this bigger wave because the waves are sort of in sync with one another, and that causes a bigger wave or a bigger amplitude to be formed, right? Now, the opposite of this would be destructive interference, where if you have, let's say, this side of the wave being negative, well, watch what happens. They're going to destructively interfere with one another. If I actually zoom in or slow down the footage, you can see there's like a moment in time where it's just completely flat. These waves just completely cancel each other out, and then after that, it gets back to normal. All right, it just completely cancels each other out at a specific moment in time, and yeah, just goes back to normal. Now, I want you to take a look at a specific point, and this specific point is going to be the middle. All right, watch the middle, okay? So when I play this animation, just watch the middle point, right along here, all right? Notice how the middle point always stays at 0, right? No matter where I am in this destructive interference, the middle part is always sort of at 0, right? It's always canceling out with one another. You see, any point during my waves sort of meeting each other, this point right over here is always at 0, and that point is called a node. It's basically a region where, a node never moves, right? It's just a point that always stays stationary no matter, where your waves are in this sort of interference, okay? So these nodes, they occur due to destructive interference, and this is between two waves that are traveling in opposite directions, okay? So that's that. Now let's talk about a little bit of lasers, all right? And speaking of lasers, these are laser lights. So all of this is light, and you just play around with it, and whoa, what the hell is this? So light can do, three things, all right? So three things can happen to light. Of course, light can be absorbed. Light can be, let's say, reflected, and these two you probably know. But light can also be refracted, which is a new concept that we're going to explore. All right, now there's reflected and refracted part. We're going to focus more on that rather than the absorbing part. So yeah, in my simulation, you can see that some of light is being reflected, as you can see, right? Some of light's being reflected, and then this ray that just suddenly appears out of nowhere, that's the refracted light. Now you can see that on the top here, I have a material, and right now, let's just say that I have glass, right? And at the bottom, my material, let's just say that's air, okay? Now you can see that as light travels from sort of one material to the other material, it's going to refract. Not always, right? It actually, it's really weird because it actually depends on the angle at which you point the light. Sometimes if you point the light at a certain angle, it might not refract. Sometimes it will refract. Don't worry, we're going to get to all of that later. But this is just something really cool. Now, you see this index of refraction here. And what does the index of refraction tell you? Index of refraction is just the ratio between the speed of light in a vacuum and basically the speed of light in whatever material that you're looking at. So if I, in this case, have an index of refraction of 1.5, all this is telling me is that the speed of light in a vacuum is 1.5 times faster than the speed of light in glass. All right, if I have a speed of light of water, or sorry, my index of refraction is of water, which is 1.33, all this is saying is that the speed of light is going to be 1.33 times faster in a vacuum than in water, right? Now, the speed of light, right, it's the fastest thing. So, of course, the index of refraction can actually not be less than 1, all right? The index of refraction, this n value, cannot be less than 1, all right? And the reason why is that would imply that the speed of light is actually slower in a vacuum than whatever material that you're looking at. And of course, the speed of light in a vacuum is, the fastest thing, right? Nothing can beat it. So, that wouldn't make sense that your index of refraction would be less than 1, right? You see in the simulation, you cannot go below 1, all right? Let's take a look at some other stuff. Specifically, reflection. Like when light is being reflected, right? You can see that there's this line drawn here. And this line is called the normal line. Think about the normal force. It's going to be perpendicular to, whatever surface this light is bouncing off of, right? And basically, when you have this normal and you have this light hitting it, and the light is being reflected, it turns out that the angle at which you're sort of pointing the light, which we call the angle of incidence, is going to be the same as the angle of reflection. So let me just write this down here. So let's say this is my laser. I point it down to my surface, and it reflects it, right? And then this, of course, would be my normal. And all this is saying is that the angle of incidence, which I'm going to call just theta I, that's going to be equal to the angle at which this is being sort of reflected. So this angle right over here, angles. Now, if we were to compare two indexes of refractions and sort of tell you what they mean, well then, this index of refraction of 5.5 just tells me that the speed of light is going to be 5.5 times faster in the vacuum than in my sort of material. While this one, it's only 3.5 times faster than in my material. So you would expect that, the speed of light is slower or in this material than compared to in this material right over here. And another way to kind of describe this is that, well, you would say that this material is sort of denser, all right, than this material right over here. Now, why does this make sense? Well, if the speed of light moves slower in a material, that means that the material is like very dense, right? It's sort of stopping the speed of light more than in this other material, which is not as dense. So that means that it does not really kind of stop the light, or it kind of lets the light move a bit faster. It doesn't stop it as much. Now, if you actually want to find the angle of refraction, there's actually a very nice formula. And this is something known as Snell's law. And Snell's law basically tells you if you have index of refraction for a material and you have the angle of incidence, or the angle of the light beam, that's going to be equal to the index of refraction for the other material multiplied by sine of, the refracted angle. All right. So let me just give you an example here. Let's say that light goes from air to, let's say, I don't know, water. let's say light goes from air to water. And let's say that you point this at an angle of 30 degrees. And you want to find out the angle of refraction, which is this angle right over here, right? Because, I mean, the angle of reflection would be this angle, but then the angle of refraction would just be this sort of bottom angle here, right? And you want to find the angle of refraction. So here's what you do. Remember Snell's law, sine of the angle of incidence, that's going to be equal to the index of refraction for the second material multiplied by sine of the angle of my refraction, okay? So light goes from air, which has an index of refraction of 1, and then we're pointing this at 30 degrees. That's going to be equal to, well, the index of refraction for water is going to be 1.33, right? Because, right, that's the index of refraction for water, that's 1.33. And that's going to be multiplied by sine of, well, I don't know what this angle is. Let's just call it the angle of refraction. This is what we're solving for. So then at this point, you would just divide both sides by 1.33. 1.33. This cancels out. And to find out the angle of refraction, you just get, because we're dealing with angles in degrees, remember if you have a TI-84, you have to set the calculator mode to degree mode instead of radians mode. But if you actually do that, you get that the angle of refraction is approximately 22 degrees. All right. And well, from the looks of this looks pretty damn accurate. So I would like that answer. This answer also sort of makes sense because, well, if you're going from a faster material, right? Because this has an index of refraction of 1, meaning that, well, it's basically the speed of light. And this index of refraction of 1.33 basically says that the speed of light is 1.33 times faster in a vacuum than in my material. So light is going to travel slower in my material. You can see the light is traveling fast here, but then when it reaches the other material, it travels slower, right? It's bent more, you can see, because, well, this material is like more dense, so it's gonna like curve the path inwards, right? And yeah, that's basically like how this answer should make sense, right? If you have this larger index of refraction, then it should bend the light towards the normal more, right? Than, you know, this regular sort of index of refraction of 1. Okay, I got just another practice problem for you. Let's just say light is going from glass into air. And let's say that this is about a 40-degree angle. N1 is 1.5, N2 is 1. All right, so let's just get that clear first. This is 1. We said that we have a 40-degree thing, 40-degree angle of incidence, and we're trying to solve for the angle of refraction. So now we could just take inverse sine on both sides, right? Just take inverse sine on both sides. You know, this is going to cancel out. And putting this into my calculator, okay, I actually got about 74.4 degree angle for my index of refraction. And that looks pretty damn right. All right, why is that true? Think about this logically, right? If you have this higher index of refraction, that means that, well, this material is basically denser, right? The higher the index of refraction, basically the denser your material is. And yeah, the slower the light is going to move in that material. So you can see that light is moving pretty, slowly, right? You see that light is going to move pretty slowly. But then when it reaches this other material with a higher index of refraction, well, it's less dense. So it's able to move sort of at a bigger angle to the normal, right? It's going to move at a bigger angle. And this is why it sort of deviates sort of more. All right. So it makes sense that, well, the angle of refraction here is actually greater. Okay. So let's just kind of summarize what we learned from these two practice problems. So when light goes from a low index of refraction, to a higher index of refraction, well, we can say that the angle of refraction is relatively small. And what's going to happen is that our light is going to sort of bend towards this normal. So light is going to bend towards the normal. All right, towards normal. And because the light bends towards the normal, well, that's going to cause this angle of reflection. Now let's talk about the critical angle. To make this clear, the critical angle only occurs when light travels from a denser medium to a less dense medium, aka a high index of refraction to a low index of refraction. All right. The critical angle is basically when the angle of incidence that causes the angle of refraction to be 90 degrees. You can see this angle of incidence right over here causes my angle of refraction to be 90 degrees. Anything that's less than this angle, light is going to be refracted. And anything that is greater than this angle, all the light is going to be reflected. Okay? So critical angle is like this turning point, basically, where you're either reflecting after a certain point or... Alright, so here's actually how you can find the critical angle. I remember the critical angle of incidence that causes my angle of refraction to be 90 degrees. So I can use Snell's law to kind of explain everything. So I want to find out the angle of incidence that causes this refracted angle to be 90 degrees. So what I can do is, first of all, I can just divide both sides by n1. That cancels out, and I get that sine of my critical angle is going to be equal to n2 multiplied by sine of 90 degrees. But sine of 90 degrees is just 1, so that cancels out. And I get that sine of the critical angle, that's going to be equal to n2 divided by n1. Basically, the ratios between the indexes of refraction. Okay? All you have to do now is just take arc sine of both sides, and then you could just solve for the angle of incidence. But notice here something that's important. In order for this equation to work, n1 has to be greater than n2. The reason why is because, well, if you have n2 being greater than n1, all of this is going to be greater than 1, right? Let's say if n2 is like 2 and n1 is like 1. 2 divided by 1 is obviously greater than 1. However, when you look at sine of an angle, actually let me go to decimals here. When you look at sine of an angle, it can only be, the maximum value of sine is 1. If sine of an angle is greater than 1, then kind of the solution does not exist, right? Sine of an angle cannot be greater than 1. And therefore, this is actually why you actually have to go from a higher index of refraction to a lower index of refraction. Let's say if I have 2 indexes of refraction, okay? And this is going to be caused by different velocities, right? So if this is material 1, the velocity at material 1 is going to be different from the velocity at material 2, let's just say. And that's going to cause 2 different indexes of refractions, right? Because remember, index of refraction is the speed of light in a vacuum divided by the speed of light in whatever material you're looking at. Now, if I divided, these indexes of fractions and everything by each other, these are still going to be equal to each other because n1 is equal to c divided by v1. So you're essentially dividing by the same thing on both sides, right? It's like if you have 5 is equal to 5, and you divide both sides by 5, you're gonna get the same result of something is equal to something. Anyways, we're going to get n2 divided by n1 is going to be equal to, well, let's actually rip apart this fraction. So remember, this is c divided by v2 divided by c divided by v1, right? And this is basically this fraction right over here written in like a much clearer way. And keep, change, flip, right? So I'm just going to keep this, and I'm just going to flip this. Notice how the speed of light sort of cancels out, and I get that v1 divided by v2 is actually going to be equal to n2 divided by n1. All right. Now remember, when light is traveling from, let's say, one material to the other, of course it's at an angle, at a specific angle, it's gonna like refract. But also, when a light travels through one medium to another medium, the wavelength of that light changes. Remember, velocity from your reference guide, velocity is equal to frequency multiplied by the wavelength. And the thing is that when you're going from one medium to another, the frequency actually does not change. The only thing that does change is the wavelength. So the frequencies are equal to each other, but let's just call this wavelength 1, and let's just call this wavelength 2. So imagine if we, once again, I see this v1 divided by v2, so what I'm going to do here is I'm just going to divide v1 divided by v2 on everything, right? That's just what I'm going to do. I know that from going one material to the other material, the frequencies are going to be the same. Therefore, v1 divided by v2 is going to be equal to the wavelength of, light 1. So therefore, v1 divided by v2 is going to be equal to the wavelength of my light at that first material divided by the wavelength of my light at that second material. And I can write this here as well. It's going to be equal to lambda 1 divided by lambda 2. And luckily for you, this is also on the reference guide, so you're chilling. I have a pendulum here, and this is probably the first physics lab you're going to do. And basically, look at this. That is one cycle for the pendulum, all right? So you can see that when you drop this pendulum, it takes some time for it to complete one cycle. One cycle would be considered that. All right, that's one cycle. The amount of time it takes for it to come back to its sort of original sort of starting position, which was right here. All right, and I have a couple of factors that I can change. I can change the mass of this bob, that's what you would call it. I can change the length of the rope that's hanging this bob, and I can also change, we're gonna ignore gravity for now, but I can also change the angle at which it's dropped. So maybe if I drop this at 45 degrees, maybe this will take a shorter amount of time than me dropping it at 90 degrees, because at 90 degrees, notice how it has to travel more, but at 45 degrees, it doesn't have to travel as much. So I'm going to tell you that only one of these things, or one of these factors, actually influences how long it takes for this to complete one cycle. And I want you to guess which one that is. And just a side note that right now, what we're essentially doing is we're trying to find out what factor, in fancier terms, what factor affects the period of the pendulum. Remember, period is just how many seconds does it take for you to complete one cycle, right? How many seconds does it take for you to complete one cycle? And we're trying to find out what factors affect this. So the answer is actually the length. The length will actually affect the amount of time it takes for, well, you to complete one cycle. In fact, a larger length, it takes pretty long to complete one cycle. But if I have a shorter length, yeah, that's definitely way faster than this, right? Let's be honest here. So why don't the other factors work? Why doesn't me dropping this thing from a higher angle actually affect the amount of time it takes for it to complete one cycle? All right, and that's where we're going to actually dive into. Now, let's say if I have this mass, right, at 0.1. All right, now let's increase it to 1.5. Literally no change at all. All right, why is that? Because remember, from your reference table, if you go back to your reference table, you actually see that the acceleration due to gravity, remember the acceleration due to gravity, I'm just going to write AG, that's going to be equal to 9.81 meters per second squared. Remember, gravity, this acceleration due to gravity is actually a constant on Earth, right? It's a constant, meaning that no matter what type of object you have, no matter how heavy or how light the object is, it's going to accelerate at the same sort of rate, right? It's going to accelerate at the same rate. This is why, when you drop a bowling ball, and let's say a small bowling ball from the same height, it's actually going to fall to the floor at the same time, right? Because the acceleration due to gravity is the same. And we actually talked about this in one of my previous videos. But the thing is that, maybe I'll reiterate this, but even though the force of gravity on this big bowling ball is obviously greater than the force of gravity on this smaller bowling ball. However, the bigger bowling ball has more inertia, and that actually balances out with, well, the force of gravity, which is why the acceleration due to gravity is a constant, okay? Think back to force is equal to mass times acceleration. Even though the force of gravity is bigger, well, my mass in this bigger bowling ball is also bigger, and that actually balances out, leading to a constant acceleration. So I actually got two pendulums. Now this second pendulum, I'm dropping it at a 45-degree angle. This one, I'm dropping it at a 20-degree angle. And they're all going to have the same sort of scenario, but the only thing that's different is the angle. Now, if you look, they both take the same amount of time to complete one cycle. The reason why is because even though the second pendulum is at a higher angle, right, relative to, you would actually call this, it's like a vertical reference essentially, right? Because like you're measuring the angle relative to this vertical reference that you kind of started at, right? And you see that even though this second one is a little bit higher, meaning that it has to travel more, right? You can see that it has to travel more in order to complete one cycle. Well, the second one also has higher potential energy, right? Because it's at a higher angle, it has more potential energy. You can see this one is clearly higher than the first bob, right? And therefore, more potential energy means that more of that will be converted into kinetic energy, which means that, well, the amount of times it takes a complete cycle, that will balance out. In simpler terms, the second one is higher, it's going to gather more speed, and therefore, well, that's actually going to balance out the distance that it has to travel. So it actually turns out that the period of the pendulum is equal to 2 pi multiplied by the square root of the length of that string that we kind of saw, and also divided by the acceleration due to gravity. And another factor that, well, this is actually another factor that we didn't actually talk about, because, well, you can see that in the formula, If I increase the length, I also increase the period, because length is in the numerator. So higher numerator means that higher value. But if I increase gravity, well then my period decreases because gravity is in the denominator, so it's going to make my value smaller. That makes sense, right? Imagine if I increase the acceleration due to gravity. So basically, my bob is essentially going to accelerate faster. If I'm accelerating faster, it's going to take me less time for me to complete my cycle. That's exactly the case here. I set my gravity equal to lots, and you can see that. It takes a very, very short amount of time for one period compared to a gravity of, let's say, close to none, which, think about like zero gravity scenarios, right? Basically floating at that point. So first, we have mirrors and lenses. Now, the difference between a mirror and a lens is that mirrors reflect light, while lenses, they kind of let light pass through, but like they kind of bend it in a way. So as you can, this is lens, this is mirror. Lens, they allow light to pass through, but it like bends in like a weird way. While mirror, they reflect the light, right? They reflect the light. Now let's start off with just a regular old flat mirror. And the flat mirror, well, it's literally what it sounds like. It's probably the mirror y'all have been dealing with your whole life. This is something known as the principal axis, or this line, this dashed line, or dotted line that you've seen here. And this is basically just representing something known as the principal axis, and that's just like a line through the center of the mirror. All right. Now, these flat mirrors, they form something known as a virtual image. All right, an image that's, well, not real. It's virtual. And you might be saying, well, that kind of makes sense, right? Don't all mirrors sort of do that? They create virtual images? And I'm here to tell you that no. When mirrors actually, reflect light, not all the times does it create a virtual image. You actually have different types of mirrors, but, we'll get to that later. But how does a virtual image and how does like an actual image even form in the first place? All right. Now, as you can see, my light rays, so this is basically like my light rays, and you can see that my light rays are all diverging, right? They're kind of getting further and further away from each other. They're not actually meeting at a single point. However, you can see these dotted lines. If I were to kind of draw dotted lines so that they were to connect, well, then I would have a virtual image. So virtual images come from the fact that the light rays, they diverge. But if you were to actually, draw dotted lines, like imaginary lines, to this single point right over here, then, well, it forms a virtual image. All right. So kind of one really important thing to distinguish between like a real image and a virtual image is you just have to ask yourself the question, do I have to draw dotted lines in order to actually, view where the image is? You can see that when I'm dealing with real images, I don't have to draw these dotted lines. All of these light rays are going to meet at a single point, forming a real image. But for virtual images, I have to draw this dotted line to represent where it actually is located. Okay? So that is the first thing. Second thing is that you notice how there's like a low diameter thing. This just changes the resolution of the image. So you can see that with low diameter, well, low resolution, high diameter. Well, one of the similarities is that you have something known as a convex lens and a concave lens. And for mirrors, you have a concave mirror and a convex mirror as well. So, very similar names. But that also means that it is very easy to confuse them. So let's get started with a concave mirror. As you can see, this mirror is sort of curved inwards. So this. Meanwhile, a convex mirror is going to look like this. Okay. Now, when you're looking at these curved mirrors, you're going to see another thing called the radius of curvature, which kind of just represents, wow, there's actually something, before we get into radius of curvature, there's also something known as the center of curvature. And this is basically like, look, imagine if you have this mirror right over here, and you sort of drew a circle to like represent, this whole entire thing. So imagine if I have, let's say this is my object right over here, and let's say this is my concave mirror, and what I do is I sort of extend this so that it creates like a full circle. So let me just it's not perfect, but there it is. You can see that, well, in the circle, of course, I have the center, and the center is called, let me just write it down here, center of curvature. All right. And actually, this basically represents like the radius of curvature. Okay, so this would be the radius of curvature. So of course you can see that, well, if my mirror is curved more inwards, it's going to have like a tinier circle. So that means that the center of curvature is going to be less. But I have like a really sort of a mirror that's, well, a little less bent, then the circle would be much bigger, as you would kind of imagine. And therefore it would have a higher radius of curvature. Now, speaking of radius of curvature, half that distance is something known as the focal points. All right, so if I mirror here, and half this distance, so I can say that, of the focal point, or 2 times the focal point, is equal to the radius of curvature. For concave mirror, the focal point is going to be located at the side that, the mirror is sort of cusping, I guess you can say. All right, so this would be, it would be like in this side right over here, right? This is where the focal point will be located. And you can see, of course, because changing my radius of curvature changes my, or, changing how this mirror looks, that changes my radius of curvature. And therefore, changing the radius of curvature changes my focal point, right? Because focal point is just going to be half that distance, all right? Another interesting relationship that you can see is that if my object distance is behind this focal point, the image is going to be real, all right? And if I zoom out, you can see that this is going to be a real image. Real images are always going to be like inverted, all right? So they're going to be like flipped. And it's always going to be like, I guess you could say like upside down, and it's like below where the actual object is. So you can see the actual object is like, you can see that's above my principal axis, but for my real image, it's going to be upside down and it's going to be below my principal axis. You can see that if I go past the focal point, then I get the virtual images. Then you see these dashed lines here, and if I go past the focal point, then I get my virtual image. So that is actually very cool. All right. Now let's talk about convex mirrors. The first thing that you might notice is that convex mirrors, their focal point is, well, right over here. And the reason why is because, well, convex mirrors, they only form virtual images. All right. So if you have convex mirrors, they're always going to form virtual images. And it doesn't really take that much explanation to explain why. Let's say this is your object here. Convex mirrors are shaped in a way where if any sort of light sort of hits my mirror, they're all going to get deflected in different directions, right? They're all going to get deflected in different directions. So they're never going to converge. They're never going to converge, right? And instead, they're going to diverge. But however, if I draw like imaginary lines, so once again, you can see that because I have to draw imaginary lines, my image is virtual, right? And they're all coming from this sort of single point. Well then, convex mirrors, they're always going to form virtual images. And that is exactly the case here, all right? It doesn't matter where it is, it's always going to form virtual images. Now we can get into convex lenses, okay? Okay, so you can see that I have drawn a convex lens, and it sort of looks like a rhombus, while a concave lens, it sort of looks like an hourglass. Let's get into it. Convex lenses, they can form real images or virtual images. One big difference with lenses and mirrors is that because lenses, of course, they let light through, right? Mirrors reflect light, but lenses, they let light through. So you can see that real images will now form on the opposite side, right? Because it lets light through, while the virtual images will now be on the same side as the object. So this is going to be the mirrors that we've seen where the virtual images, you just look at yourself in the mirror, and the virtual images is always going to be on the opposite side of what you're sort of expecting. But for lenses, it's going to be the same size because lenses, they let light through, right? So if the light were to sort of, right, you can see that the lenses let light through. So if the light rays were to sort of converge from a single point, it would be on the same side as this object right over here, okay? Now, lenses, another thing that you notice is that they have 2 focal points, all right? And that's another property of them. Mirrors only have 1, lenses have 2. Convex lens, as you can see, well, they sort of direct light all in sort of this one point right now, but you can see that for concave lenses, it's only virtual, right? So while convex lenses, they can be real and virtual, concave lenses can only be virtual. So concave lenses can only be virtual. And actually, that's the same for the convex. This is the convex mirror, and this is also virtual. I forgot to write this down. But the concave lens is like the convex mirror. They can only be virtual. So you can see how mirrors and lenses is very confusing because they freaking flipped the names. All right, so you have to remember that convex mirrors and concave lenses, they only form virtual sort of images, while concave mirrors and convex lenses, they can form virtual and real images. Okay, so that is another important thing to know. Now, another thing you might notice is, well, for this mirror right over here, and take a look at this, you have index of refraction. Wow. All right. This index of refraction also plays a very important role in if the image is going to be real or if it's going to be virtual. As you can see, if I decrease my index of refraction, it looks like my focal points are getting further and further away, and it's going to be so far away, and the light rays are going to be so sort of divergent that, well, it's going to form a virtual image, and it's all going to meet up. These light rays are all going to meet up here. All right. Now, why does index of refraction affect where the image is located? I'm not actually going to get into the formula for this in this video, but just know that the power of a lens depends on its index of refraction. And you can see the more I increase my index of refraction, the more you'll see that the light sort of bends. And so yeah, that's pretty much it. Remember, the radius of curvature, that sort of changes while this circle, this imaginary circle that I'm creating with this like lens, it also applies for mirrors as well, and therefore changing the radius of curvature changes focal length. All right, so low radius of curvature, the image is going to be real next to you because the focal lengths are going to be closer as well. Index of refraction, that changes how much this lens bends the actual light, and remember diameter, that just affects, well, how sort of the resolution of the image, right? So low resolution, high resolution. Okay. Now we can talk about something known as ray diagrams, and let's draw them for mirrors first. Mirrors. Okay. So let's say this is my principal axis, like this. Okay. Principal axis. And then let's say that I have a mirror. So this is my mirror. And what shape is it? Well, this is going to be a concave mirror, right? So concave mirror. And the center of this mirror right over here is actually called a pole. It's like a North Pole, South Pole, right? This is going to be called a pole. Let's say this is my object. And you just represent the object with like an arrow, right? And then this arrow basically represents like the height of the object, right? And to do this, well, remember, concave mirrors, they always have a focal point that sort of, it's like this is Pac-Man, right? And then Pac-Man is eating the focal point. So the focal point is always going to be inside this cusp for the mirror, okay? That's how I like to remember it. Now, for the rays of light, well, I know for a ray diagram, sometimes you're, depending on who's teaching you, like, you can have like 3 rays, and then, the ray diagram is like, involving 3 rays. But, I like to do it with 2 rays, and you'll find out, online resources. There's also 2-ray, diagrams. And yeah, that's like the one that I like to use. So remember, the only thing that you got to remember is that parallel to focal, and then focal to parallel. That's really all you need to remember for drawing the ray diagrams. First of all, you're going to draw a parallel line to the principal axis, and then because this is a mirror, the light is going to be reflected, and it's going to be reflected back to this focal point for mirrors. And then the second ray that you're going to draw, it's going to be from the focal point. It's going to be going through the focal point, right? And then it's going to be parallel. So it's going to be like this. Now take a look at any intersections besides the focal point, of course. And you'll see that the intersection is this. All right. Therefore, my image is real because my image is a real image because remember, this image is like upside down, right? It's below the principal axis. For a convex mirror, this is very similar process. Remember, parallel to your focal point. So first, this is your object here, and it's going to go parallel and then to the focal point. But the problem is that, remember, in a convex mirror, it's shaped in a way where it's actually going to deflect the light, right? It's going to deflect the light. However, we can draw an imaginary line to the focal point. Ah, I see where this comes in. And, that's, the trick to doing mirror diagrams for convex mirrors, right? Or ray diagram for convex mirrors. You have to draw this imaginary line to the focal point that has to line up with, everything. Okay, and then for the second ray, all you have to do is you just have to follow the same rule. Remember, focal point to parallel. So what I'm going to do is imagine if I'm drawing like a line towards the focal point, right? And then, in reality, what would happen to this piece of light is it would get deflected, right? It would get deflected parallelly, right? Because this is focal point to parallel, so it's going to get deflected in a parallel way. However, if we were to imagine this virtually, what happened in the virtual world? Well, in the virtual world, this piece of light right over here would meet the focal point like this, right? This piece of light would meet the focal point like this, and then this parallel piece of light would also, extend. And then notice how there's this intersection point right over here, right? We're obviously looking at intersection points that are not the focal points, right? Because, yeah. So right over here, this is going to be my new virtual object. And that's how you draw the ray diagrams for convex mirrors. So your first ray, it's going to sort of bounce off this mirror, right? It's parallel to focal point, but when it bounces off, you also have to create this imaginary line towards the focal point on the other side. For the second ray, you draw from, this ray is sort of heading towards the direction of the focal point. You can see it sort of cuts through. Imagine if it cut through this mirror into the imaginary realm. Well, it would go to this focal point right over here. And then when it, shoots back parallelly, right, from focal to parallel, well, then it's also going to extend to the other side. And there should be an intersection point. Also note the height of the object, right? The height of my original object is, well, taller than the height of my image. And soon we're going to get to a concept called magnification. And you can see that, well, this object is, well, demagnified. All right, I know that's not the correct term for it, but let me just say right now that it's demagnified, all right? Meaning that, well, it got short. Now for lenses, the simulation does an amazing job at explaining this. So what happens is that the first ray that you're going to draw is going to be, once again, it's going to be parallel to your principal axis, and it's going to go through the focal point. The second ray that you're going to draw is just going to go straight through the center of the lens. And then the third sort of ray that you're going to draw, well, it's very similar, right? You just go sort of through this focal point, and then you go parallel. So you kind of see the pattern there, some similarities. And, well, they're all going to intersect at this one point. So, of course, you can see that this point is below our principal axis, which means it's a real image. And in addition, for lenses, remember, real images actually appear on the opposite side because, well, if you have light rays, right, and they pass through the lens, they let light pass through. So the only way that, the light will converge is if it's on this side right over here. Now, with the image, and by the way, this is for a convex lens, by the way. If your image forms a virtual image, well, then in order to draw the ray diagram, your first ray is, well, it's going to be the same as, usual, right? You're going to draw it to sort of the top of the lens, and then after that, it's right parallel to the principal axis, and then it's going to go through this focal point. The second ray, it goes through the center, and the third ray is where it gets a little bit weird. And actually, instead of drawing it like this down here, which you can do, there's actually like an easier way. So I'm actually going to draw here. So let's say this is my lens, right? This is my lens. And this is for the scenario when, this is your focal point, let's just say. This is the opposite focal point on the opposite side. And let's say this is your object right over here. All right. Now, we said how the first ray of light, so what does the first ray of light do again? Remember, it goes parallel through focal point. So that's what we're going to do first. It's going to go sort of parallel and then through that focal point. Okay. What about the second light? Well, the second light just goes straight through the center. So those two things sort of stay constant, right? If this is your pole, center, well, then that's just gonna be the same. However, the third ray of light, what you're gonna do is you're gonna start from the focal point, and you're actually gonna draw an imaginary line upwards. imaginary. We're just going to draw this line upwards until it sort of passes this lens, and then you're going to draw it parallel. So remember, this is focal to parallel. So that this kind of also is like a pattern that we see. Remember, the first ray, it's parallel to focal. The second ray is through the center, and then the third ray is focal to parallel. And you can see that, well, all of my rays, so this ray right over here, this top ray right over here, all of these intersect at this single point that we see, right? And even this ray right over here, even this ray right over here, right? All of these intersect at a single point. So, I mean, so that's also another way to do it. So we draw this imaginary line. You can imagine this imaginary line from our focal point all the way up, right? Now, for a concave lens, well, this is going to be a little bit different. And this is actually going to be a little bit different from what the simulation sort of ray diagram shows. All right, this is another way. So concave lens, we're going to draw a couple of lines here, right? Remember, it goes from parallel, but this time for concave lens, it deflects the light up, right? Because for a concave lens, all the light diverges, right? They all go in different directions. So the first ray is going to just go up. The second ray is just going to go straight towards the center. Yeah. Just going to be like that. So first ray, you go parallel, then it diverges. Second ray, you just go straight towards the center. And then the third ray, well, this is where it gets a little bit tricky. And now what you want to do is you sort of want to draw a line from this object to the focal point. So something like this, right? But the problem is that we're dealing with, remember, this is a concave lens. So instead of the light just going straight towards the focal point, it's actually going to just go straight to parallel, right? So I'm gonna just like replay that. I'm gonna just replay that for a bit. So right, you sort of draw the line as if it was going towards this focal point, right? But then because of this concave lens, well, it's actually going to be bent just parallel. So that is how you do it. Now, if your light rays all go in different directions, then that's kind of how you know that you've done something right. If all your light rays are converging to something and you're dealing with a concave lens, well, that's a really easy way to tell that something has gone wrong. Okay. And now, well, you can see that if I were to draw like virtual, so these are my virtual rays now. So this is my first virtual ray. This is my second virtual ray. And on this dot, so we don't really need to emphasize that. I know this isn't like perfect. This is like a little bit slanted, but imagine if this like was completely straight. It would also be on this, like near this area right over here. So you can see that all of these light rays meet in this one area, and that's where your virtual image is. Notice how it's upright, and it's at the same side as your object, which makes sense because this is a concave lens. So for lenses, virtual image is on the same side as the object. That's how you know you did something correct. Now, here's the sort of formulas you gotta know. This is on your reference guide as well. So this is going to be 1 over the focal length equals 1 over the distance, the object distance, plus 1 over the image distance. And then this is also the magnification formula down here. And this is basically telling you, well, is the image getting bigger, right, compared to the object, or is it smaller, aka diminished? So remember, height of image divided by height of object is equal to negative of the distance of image divided by the distance of the object. And basically sign convention is just like, what sign do you use when representing like a distance or height? Now, let's say that this is my principal axis. So let's say that this is my principal axis. All right, and let's say that light is coming towards this way. Whatever side that the light comes towards on, well, actually, let's talk about heights first. Heights might be easier. So when you have an object, if it's above the principal axis, it's going to be positive. If it's below, it's going to be negative. All right, simple enough, right? And this goes for, images as well, right? If it's above principal axis, positive, below, negative. And it follows this sort of Cartesian plane thing, right? Where you have your, x and y axis. And if it's above, well, then your y-axis is positive. If it's below, your y value is negative. Okay. Now, when you're dealing with like distances and stuff, right? Like object distances, image distances, focal lengths, right? These are all x sort of direction features. And for x direction features, well, everything sort of to the left is going to be negative, right? Everything that's on the same side as the direction that the light is coming towards is negative, just like in a Cartesian plane. And everything on the other side
is going to be positive. So using that information, let's do a practice problem. Okay, I just stole this problem from Khan Academy. So you have Olivia is inspecting the concave primary mirror of the Hubble telescope before it's launched into space. She stands in front of a mirror which has a focal length of this. What is the image distance of Olivia's image? So now we're going to be dealing with a concave mirror. Now remember the shape of the concave mirror. It's bent inwards, right? It's bent inwards. So she stands 87 centimeters here, and the focal length is 58 centimeters. All right, and then we want to find out the image distance. Now immediately, I know that whatever answer I get, I know that it has to be a real image. All right, I know that my distance image has to be on the same side as, these two distances. Remember, if your object for a concave mirror, if your object is, before the focal length, well, then it's a real image. If it's past the focal length, that's when it becomes virtual. So already, because my object is behind this focal length, I already know that I should get a value that's like, somewhere around here, right? And that's going to make sense. Okay, now I'm just going to bring this formula down here so y'all can see. And let me just bring this right over here. Okay? So now this is just literally just plug and chug. But we have to remember that light is coming towards this direction, right? And it's shining through the mirror and everything. Now, these distances are actually going to be negative because it's in the same sort of side as where the light is coming from. So remember, the same side that the light is coming from, every distance here is going to be negative. On the opposite side, however, these distances would be positive if there were any, distances on this side. So just keep that in mind. So you're going to have 1 over the focal length, which is negative 58, is going to be equal to 1 over the distance of the object plus 1 over the distance of the image, which we don't know, so let's just put the distance of the image here. Okay, I just put that into my calculator and everything, and I got that the image distance is equal to negative 174 centimeters. And that answer makes sense because, remember that negative values mean that, it's on the same side as the light. So negative 174 would land here. And therefore, this would be a real image because it's on the same side as, the other values here, right? If you have a real image for a mirror, it's on the same side as the, direction of where the light, is coming from. If the question asks you to find out the magnification, you just do negative of negative 174 divided by the distance of the object. Well, the distance of object, they give you it, right? It's negative 87, right? So it's 87 centimeters. So if you put this into the calculator, this value is actually negative 2. And what does this mean? So the magnitude of, magnification, I know that sounds weird, but you can see, just looking at, just ignoring this sign right over here, if you just look at the magnitude of your magnification, this 2 right over here just tells me that, my image is going to be 2 times sort of taller, right? It's going to have a height of 2 times compared to my original image. Or, sorry, compared to my original object. So if my object was, let's say, like this, my image would be twice the height. This negative sign in front, that tells me that, this image is going to be flipped 180 degrees. So it's going to be like this. And always ask yourself, does this answer make sense? Yes, it does. Because remember, real images, they are inverted, right? They are upside down. They are below the principal axis. So they're going to have a negative sort of magnification, right? You're going to have a negative height. So this is going to be like negatively magnified, right? It's like this scenario right here, where like the object distance is here, reflects, and then you have this sort of real image that's below the principal axis, so the magnification is negative, and it got bigger, which is why the magnitude of the magnification is, greater than 1. Now for lenses, it's actually a little bit different. So this is the formula for mirrors, okay? So for mirrors, this is the formula. However, for lenses, you're going to use a slightly different formula. 1 over the focal length is equal to 1 over the distance of the image minus the 1 over the distance of the object. And then for the magnification formula, it's the same, except you don't include the negative sign. All right, so those are like tiny differences that you just kind of have to know. Okay, so we know that our object has a height of 4 centimeters, and it's placed 15 centimeters in front of a convex lens. So what is a convex lens? Well, this is convex lens looks like this, right? A little rhombus, and it's like 15 centimeters, right? And we know that it has a focal length of 9 centimeters. Now, for convex lenses, the focal length is going to be positive. Okay, so this is going to be 9.0 centimeters, and yeah, there we go. So yeah, remember that because the rays of light are going this way to the right, everything that's to the right of our mirror is going to have a positive sign in terms of distance. This is going to be positive 9 centimeters, while everything to the left is going to have negative sign. Sorry, negative sign here in terms of distances. For height, it's just if it's above or below the principal axis. But for distances, you just have to look at, the direction of where the light is going. So let's actually, do this problem, and we want to find out the height of the image. So the height of the image here. Now, we know the height of our object is 4 centimeters. If I find out the magnification of my object, well then, if I know these two variables, and I know this variable here, well, I can solve for the image height. Now, how do I actually get the magnification formula? Well, I have to solve for the distance of the image. So you see, this is a two-step problem. I solve for the distance of the image, then I have the distance of my image, I have the distance of my object, and I also have the height of my object, which that's given to me in the problem. So then, once I know these three variables, I can solve for the fourth unknown variable. So let's do that. 1 over my focal length, which is 9, is equal to 1 over the distance of my image, which is negative 15 centimeters. Or sorry, that's our unknown. And see, it's very easy to get confused with this stuff. And this is going to be minus 1 over the distance of my object, which is negative 15 centimeters. Now, after that, I just have to subtract 1 over 15 from both sides. And when I actually do that, I get that, well, my image distance is equal to 22.5 centimeters. So now I know that the distance of my image is 22.5 centimeters. I know that the distance of my object, well, that's negative 15, right? Centimeters. So therefore, I can solve for the height. I can solve for the height of my image. So let me just put this into my calculator. Actually, 22.5 divided by negative 15 is my answer, negative 6.0 centimeters, after I just plug everything into my formula. And actually, it turns out that, 22.5 divided by negative 15, that actually gives me a value of negative 1.5. And that's actually the magnification. That's actually the magnification for my image. Right? Because remember, magnification is di over do. So if I just evaluated, if the question was asking us what is the magnification, well, you would just divide these two values and you would get negative 1.5. All that means is that, well, my image would be 1.5 times sort of larger than it was at the beginning, but due to this negative sign here, it would be like flipped. So it would be a real image, meaning that it would be like inverted, right? It would be upside down below the principal axis. Now, one of the most important things in these type of problems is being able to identify if your answer makes sense. Okay, so we got that the height of our image is negative 6, and that it is located at 22.5 centimeters. So 22.5 centimeters is right here. Why does this make sense? Recall that remember that our focal length is our focal length is 9.0 centimeters. However, for lenses, remember that there's two focal points. So if I have a focal point at 9.0, I also have a focal point at negative 9.0. All right, that's pretty cool. Now take a look at this. My object is located before my focal point. So you can see here, whenever your object is located before the focal point, you're always going to form a real image. Once your object surpasses the focal point, that's when you form a virtual image. And the problem states that my object is before the focal point, meaning that for my answer, I should get a real image value. And that's exactly what I get. Remember, real images, they're inverted, meaning that their height is negative, right? They're below this principal axis. And guess what? I got a negative height for my answer. In addition, the distance of my image is 22.5 centimeters, meaning that my image is located somewhere here along the positive direction. And when you take a look at the simulation, my real image is located in the positive direction, right? If the light is coming towards the right, well, everything to the right of this lens is going to be considered positive. So this distance right over here would be positive as well. So very important to be able to identify these relationships. Encourage y'all to play with the simulation and do Khan Academy problems on these lenses and mirrors. And yeah, this is very hard to meet, so good luck. Free fall occurs when the only force acting on your object is gravity. So let's say if we have a rock, let's say if it's 80 meters above, and let's say if it was dropped. All right, so the stone, let's say if this was like, this is me up top here. I was originally holding the stone. However, when this stone is dropped, what that essentially means is that it was originally at rest, but then it was like dropped. All right. Now, based off of all this information, that the stone was at a height of 80 meters, I dropped the stone. I want to find out how long does it take? How long does it take for the stone to hit the ground? And well, we can use kinematic equations to solve this. Now, free fall is like a sort of special case of kinematic equations. So the first thing that I kind of notice is that while I'm using this kinematic equation that involves sort of displacement and involves time and everything, and the reason why is because, well, I know what my displacement is. That's 80 meters. I know my acceleration. Well, whenever you're doing acceleration, right, and you're dealing with free fall problems, it's always going to be an acceleration due to gravity, right? Because think about it. Free fall is when the only force that's acting on your object is gravity. So the only acceleration that there is gravity. And we all know the acceleration due to gravity, right? That's 9.8 meters per second. I'm just going to break this in. It's 9.81 meters per second squared multiplied by our time squared plus. Now, originally we said that our stone was dropped. So initially our stone was at rest. Think about it, right? Before the stone was dropped, our stone was at rest. So the initial velocity is going to be equal to 0. All right, whenever you're talking about something being dropped, it's being dropped from rest, all right, in this case. So our initial velocity is going to be equal to 0. And of course, this term is going to cancel out if our velocity is equal to 0. So our equation is just going to be this, all right? Now, the thing is that in free fall problems, right, gravity is the only force that's acting on your object. So what you actually do is you actually take down as being positive. I know that's a really weird thing, but that's just like the convention. Like normally, in physics problem, you take up and to the, to the right as being positive directions, and then down and to the left as being negative directions. But in free fall problems, gravity is only, force that's acting on you. And so gravity is actually going to have a positive sort of sign. So if you're dealing with acceleration downwards, what would actually be a positive value? That's just the convention for free fall problems. So now we can just, divide both sides by, whatever this value is right over here. And then we can just square root both sides after that. And then we can get our answer. I got around 4.03 seconds. Now, let's say if there was like a part two to that question. Let's say when we drop the stone, we want to find out the velocity of like the stone just before it hit the ground. So let's say if the stone is like falling, or like this rock, right? It's falling just before it hits the ground. What is the velocity of this? And, using the time it takes for this to, hit the ground, we can actually calculate that velocity. So recall this kinematic equation. Velocity at the final state is equal to the initial velocity plus the acceleration multiplied by time. Now, we said how our initial velocity was 0. So that basically can go away. And we just get that the final velocity is just the acceleration multiplied by time. So if it takes 4.03 seconds in order to fall to the ground, and the acceleration is 9.81 meters per second squared, well, we just have to multiply these two values out together, right, to get our final velocity. And then when you do so, you're going to get around 40 meters per second, or more precisely 39.6 meters per second as your velocity. So and remember that because we treat downwards as a sort of positive direction, so it makes sense that my velocity and my final answer is positive, right? A projectile is launched up with speed 10 meters per second. So, this is pretty much like velocity that they're giving us. Because, like, if we have, like, a projectile here, and it's being launched up, right, you're given the direction, which is straight up, and we know the magnitude, which is 10 meters per second. So this is essentially our initial velocity, right? 10 meters per second. Now, it's important to understand that, well, in like all physics problem, speed isn't always going to be like equal to velocity, of course. Like speed cannot be like negative, however, velocity can be negative depending on the direction. But, in these intro to, projectile problems, when they're saying, launch speed is, let's say, 20 meters per second at maybe some angle or some direction, they're really just giving you the magnitude of the initial velocity vector. All right. And this is what's actually going to allow you to use your kinematic equations to solve. Anyways, we want to find out the total time in the air. So what's going to happen is that, well, this projectile, it's going to go up, right? However, gravity at the same time is going to be pulling it down. So it's going to get to a point where it reaches its maximum height. And when the object reaches its maximum height, its velocity in the vertical direction is actually 0, because it's transitioning from going upwards to downwards. And in that specific moment in time, when it reaches its maximum height, the velocity is 0. So that's one important idea to know. So it's going to be like going up, and then when it's like changing direction, that instant when it's changing direction, reaching its maximum height, its vertical velocity is 0, and then it goes back down. And we basically want to find out, well, how long does it take for this ball to, fall back down on the ground, right? What is the total air time? So how do we solve this? Well, we have to use the kinematic equation, and we're trying to solve for time. So we know that we're going to have to use one of those kinematic equations involving time. What else do we know? We also know that our total displacement is equal to 0. Because think about it. You're throwing the ball up into the air, and it comes back down to the same spot, right? It lands, right? If you're throwing the ball straight up, right? You're throwing the ball straight up, and it lands back down. Well, its total displacement in the y direction, in the vertical direction, is going to be 0. So therefore, displacement is equal to 0. And we also know that our acceleration is equal to, well, negative 9.81 meters per second squared. Remember, for free fall problems, you want to treat downwards as the positive direction. But in this case, when we're talking about projectile motion, usually that's going to involve the projectile going up, and then the projectile is also going down as well. So notice how there's sort of like an upward component, and there's also like a downward component of projectile motion, which is why in projectile motion problems, you want to treat gravity as the downwards direction, as the negative direction instead. Now, you saw that with like some free fall problems, like you have an object, and the only thing that sort of happens to the object is that it travels down. So that's when you treat gravity as being a positive value. However, when you have a scenario where you're launching an object and its initial velocity is upwards, right? You see this initial velocity is upwards, right, in the vertical direction. That's when you actually treat gravity as being a negative value, so negative 9.81 meters per second squared. All right, so that's just something you gotta know. Now, for these types of problems, you see how it involves like 2 dimensions now. So not only are you going to be dealing with the velocity in the y direction, but you're also going to be dealing with maybe the velocity in the x direction, which most of the time is going to be a constant, because think about it. If you throw the ball like upwards like this, the only thing that's going to be acting on the ball is gravity. Right after you throw the ball upwards, you give it that initial push in the x direction. There's no gravity for the x direction, right? Gravity is going to be pulling this downwards, but other than that, there's no other forces on it. So therefore, this ball right over here, as soon as you release your hands from this ball, it's actually going to become a projectile, and it's going to be in free fall. All right, so these are all the scenarios where this ball is going to be in free fall, right? The only thing that's going to be acting on the ball is gravity, and you see how in the x direction it's going to be a constant velocity. So this ball in the x direction is going to have a constant velocity, but it's the only velocity that's sort of changing is the y velocity, the velocity in the y direction. Okay. Now here are some things that you might be asked to do. So for these types of problems, you might be asked to find the maximum height, right? Which you can think about as also your displacement, right? What is your sort of displacement from where you've thrown it to the maximum height, right? What about the displacement in the x direction? You can also be asked about that. You can also be asked about how long does it take for either of these events to happen? How long does it take for you to reach your maximum height, or for your object to fall down to the ground? So these are all questions that you might be asked about, and it's important to understand that whenever you're using kinematic equations, they all have to be in the same direction. Meaning that if I were to use, let's say, this kinematic equation right over here, the velocity the final velocity is equal to the initial velocity plus the acceleration times time. All of these values essentially have to be in the same direction. So this is the final velocity in the x direction is equal to the initial velocity in the x direction plus the acceleration in the x direction multiplied by the time, which time doesn't have any direction besides being forward. So that's like the only variable that we don't really have to worry about. But other than that, you see how all of my variables have to be in the same direction if I want to use them in my kinematic equation. It's a very important idea to understand. Anyways, let's get into practice. So you remember from the second part of my physics video that, well, it's kind of like force, right? If you have like a force in a specific direction, there's going to be a force component in the x direction, and there's also going to be a force component in the y direction, right? This is the force component in the y direction. So for example, if you were given that the force was, let's say, 5 newtons, and let's say the force in the x direction is 3 newtons, that means the force in the y direction would be 4 newtons, right? Based on the Pythagorean theorem, a squared plus b squared is c squared. And likewise, if you were just given the angle, let's say this is 30 degrees, right? This is 30 degrees. And let's say that our force is 5 newtons, and we want to calculate the force in the x direction and the force in the y direction. Well, how would you do this? Well, let's see. Let's take sine of our angle, sine of this 30 degrees. That's going to be equal to the force in the y direction, right? It's going to be opposite over hypotenuse. So this is going to be equal to opposite over hypotenuse. So if we multiply both sides by f, notice how we get, the force in the y direction. So whenever you're multiplying by sine of that angle, you get the component in the y direction. And you might have guessed, if you multiply it by cosine, well, then you're going to get the force in the x direction. This is the exact same process we're going to do with our sort of velocity. So we have a projectile that's launched at the top of a cliff, and that's going to be 45 meters above the ground. So let's say this is my ground, and let's say this is my cliff, which is 45 meters. And we throw it. So this is like, let's say this is me. What I'm going to do is I have my projectile, and I'm going to throw it, right? Now it's going to be 40 degrees above the horizontal. So compared to, the horizontal component, it's going to be 40 degrees. And it's going to travel with an initial speed of 30 meters per second. All right. So just from this first part, identify the velocity, the initial velocity in the y direction, and identify the initial velocity in the x direction. Okay. I want y'all to identify that. Well, you might recall that if you take, the velocity multiplied by sine of the angle, you get the velocity in the y direction. In this case, it's the initial velocity in the y direction. So that's why I put this I here. And recall that, well, if you multiply by cosine of that angle, you may get the velocity, in this case, the initial velocity, in the x direction. Okay? So if I just put all of this stuff into my calculator, I'm actually going to get around, for the y value, about 19.3 meters per second. And then let me see, for the x value, I get about like 23. So let me just say 23.0 meters per second. All right. Okay. Now I'm here to tell y'all that, just from this kind of information right over here, just from these couple of information, I can find out all of this stuff, which is kind of crazy to me. All right. So what I recommend to do for these type of projectile motion problems is you got to create a table, all right? And the table is just going to be full of these values where this is the x basically components. So this is the velocity in the x direction, final velocity in the x direction and everything. And then on the other side, this is going to be the y initial velocity, the y final velocity, y acceleration, and so on, all right? You'll see that the only component that is not split is time because, well, it's time, all right? Now, first, we want to find out the time it takes to reach the top of the trajectory. And that just means the time it takes for you to, reach the maximum height. All right. So let's actually do that. And because you're dealing with heights, remember, height is involving what direction? The y direction, which kind of just implies that, well, we're going to use the y variables for my kinematic equations. And that's just what that implies. So let's kind of fill in a couple of other boxes here. So for the acceleration in the y direction, we know that, well, as I throw the ball, gravity is going to be pulling it down. And I know that gravity has this acceleration of negative 9.81 meters per second squared. Remember, in just free fall problems, sorry, this should be seconds squared. But in those free fall problems where, remember, you just drop the ball down, and the only kind of direction that the object is going is downwards, that's when gravity is positive. But for this problem, you're going up and you're also going down. So because it's going like up and down, well, you would define going up as being positive and gravity pulling you downwards direction as negative. So this is negative 9.81 meters per second squared. Now, how do we find out the maximum height? Well, remember that very nice rule that we talked about. Remember, when your sort of object reaches its maximum height, remember the sort of vertical velocity is equal to 0, right? So at this moment in time, our velocity is going to be equal to 0 because, right, that's when it's changing from going up to going down. And so then in this instant, when it's changing from going up to down, its velocity is going to be equal to 0. So if you recall that, well, then this is like a really powerful tool because, well, we can set up using our first kinematic equation. We can say that the final velocity, which is at this point right over here, and we said that's equal to 0, that's going to be equal to our initial velocity in the y direction plus the acceleration in the y direction, and that's going to be multiplied by time, and then we can solve for time using this. So I got 1.97 seconds for this object to reach its maximum height. Now, there is actually a little trick that you can use, not in this problem actually, for other types of projectile motion problems. Now, let's say if your object was originally on the ground and then you throw it. So you see how this is like a little bit different than this scenario where my object is like elevated, right? I'm throwing it 45 meters up already. But if your object is being thrown from the ground, the amount of time it takes for your object to come up to the maximum point is actually going to be equal to the amount of time it takes for the object to come down. Because think about it, this is a parabola. And if you remember from like algebra class, right, the two vertex of your parabola is going to be equidistant. It's going to be the same distance from essentially the vertex, or sorry, the x-intercepts are going to be equidistant from the vertex of your parabola, which is why, the time up is equal to time down. However, for this example, this doesn't work because my object is elevated, meaning that the amount of time it takes for my object to come up is actually going to be less than the amount of time it takes for the object to come down, because my object has to come all the way down to the ground, which you can obviously see is a higher distance, or it's going to be a more displacement than my object actually going up. But just remember that for scenarios where your object is on the ground and then it lands back on the ground, well, then you can use this nice specific tool to help you. And this is very nice because now that we have the time it takes for the object to reach its maximum height, well, we can actually calculate how high this distance actually is. So once again, because we're dealing with like displacement and stuff like that, well, we're actually going to have to use this second formula right over here, right? We want a displacement, right? The maximum, this height, right? So I'm going to say my displacement, that's going to be equal to my initial velocity, which I said was 19.3, multiplied by the time, which is 1.97, plus 1/2 multiplied by my acceleration. And then this is going to be multiplied by my time squared. So 1.97 squared. And I just have to solve for this displacement. And doing all those calculations, I got that my displacement is 19 meters. Specifically, my displacement in the y direction is 19 meters because we used all the y components, right? So that's going to be my displacement in the y direction. However, there's a little bit of a problem. What this 19 meters is saying is that the distance from my original starting point to the highest point right over here, so essentially this distance right over here, that's the 19 meters that I'm talking about. But notice how that's not the total height. So to find out the total height, I have to add my original height, which was 45 meters, plus that displacement. And that gives me my total. That gives me my total height. All right. So, if you're struggling with ideas like this, very, very, very good to like visualize this stuff so that it's like really clear what's actually happening and what your calculations actually mean. But anyways, I'm gonna just put this 19 meters right over here because that's the displacement. But just know that my total sort of height is going to be 64 meters. Okay, now we want to find out the total time until the projectile hits the ground. So we are dealing with time, but we're also dealing with like displacement because like we're dealing with when it hits the ground, right? And when we're talking about like displacement, we're starting 45 meters right up on this cliff, and then when it hits the ground, well, it's 0 meters, right? This is like 0 meters. So you can see how our displacement would just be negative 45 meters, right? That's our displacement from when we threw it to when it lands on the ground. And I know displacement, using this formula right over here, displacement is equal to my initial velocity. And because we're dealing with the y value, right? We're throwing this projectile, and gravity's pulling the projectile down, meaning that it's going to hit the ground, right? That means that whenever you're dealing with heights, remember, you're going to use the y y values in this table. So once again, this is going to be 19.3, and we're trying to solve for time, so time is going to be unknown here. It's going to be plus 1/2 multiplied by my acceleration multiplied by time squared. And if we move 45 to this side, so if we add 45 to both sides, well, you can see how this is going to be 0 on this side, and this is going to be plus 45. And then this is just going to be a quadratic equation, all right? And, I could do the quadratic formula and everything, but, I'm feeling a little lazy today, so, yeah. And this is going to be, let's just say this is x squared, and this is going to be plus 19.3 t plus 45. Okay, or sorry, they should be the same variable. And as you can see, if you actually use the quadratic formula to try to solve this equation, one of your sort of results will be negative, but of course you can't have this like negative time as your answer. So the only valid answer is 5.58 seconds. So I'm just right down here, 5.58 seconds. All right, that's how long it takes for this ball to be thrown and then hit back on the ground. All right, it takes a total of 5.58 seconds. Now let's find out the horizontal displacement. So we found out that it takes a total of this many seconds for it to land on the ground. Well, I want to find out, well, how far is this distance that it traveled horizontally? So in this case, I'm going to be dealing with the x direction because I'm talking about moving horizontally, which is on like the x-axis. Now, the thing is that, well, for the x direction, your final velocity is actually going to be equal to your initial velocity. It's also going to be 23 meters per second. Right? 23 meters per second. And you might be saying, what? How is that the case? And I'm here to tell you, well, think about it. If you throw a ball up, the only force that's going to be acting on it is gravity. So in the x direction, your velocity is going to be constant. It's only in the y direction that your y velocity is changing, but in your x direction, your velocity is staying constant because, well, there's no other forces. We're going to assume that there's no air resistance to, slow this ball down, which is why I can write this 23.0 meters per second. And so if we want to get this displacement, well, you might remember the formula that, well, displacement is equal to your initial velocity multiplied by time, so 23.0 multiplied by the time it takes, which is 5.58. And notice how in the second part of the equation here, we're going to be dealing with acceleration. However, as you can see from, these two values here, our object has stayed at a constant velocity. We have not accelerated in the x direction. So that means that this is the equivalent of 1/2 multiplied by the acceleration, which is just 0 because we haven't accelerated at all. It's the same velocity as before, multiplied by time squared, which is 5.58 squared. But we're multiplying all these values by 0, meaning that all of this is just going to zero out. So the key thing to note is that if you're not accelerating, if there's no acceleration, the displacement is just equal to the initial velocity multiplied by time, because the second term just completely cancels each other out, right? Just zeroes out. So if you actually do this, you should get a value around 128. So I'm just going to say like 128.3, something around those lines, 128 meters. Okay. So that is my total displacement in the x direction. And then I'm just going to write negative 45 meters for my total displacement in the y direction, because we said how, right, our ball was originally here, and when we throw it down to the ground, right, it went down 45 meters, right, because we were 45 meters up. And what was the final one? The speed and the direction just before impact. This one is a really tricky one. And also we can kind of fill in this right over here. The acceleration in the x direction is 0 meters per second because our velocity stayed constant. And now the only thing that's left to fill in our table is the final velocity in the y direction, as well as, basically the velocity in kind of the final moments. So just before impact, so just before this ball sort of hits the ground, I want to find out the velocity. I want to find out the direction of the velocity and the magnitude of that velocity. So how can I do this problem? Well, because we're dealing with initial and final velocities, I'm just going to use this formula up here. So you can see how, I almost never use the bottom formula. Like this bottom formula is when you're not dealing with time, but for these projectile motions, you can just solve all of these problems just using these first two kinematic equation. And well, we can say that the final velocity, the velocity, before this thing lands, that's going to be equal to the initial velocity in the y direction, which we said was 19.3 meters per second. That's going to be plus the acceleration multiplied by time. So my acceleration is negative 9.81 meters per second multiplied by the total time, which we found out was 5.58 seconds, right? Because that's like the total time, right? This is just before the impact, right? You got to read this problem. It's just before this ball hits the ground, meaning that it basically traveled this entire length, and therefore our time traveled was 5.58. Now, if we solve for this final velocity, you're going to get something near negative 35.4. So I'm just going to say our final velocity is equal to negative 35.4 meters per second. So that is what I'm going to put in my table. Now, this part I think you guys are going to love, because this just encapsulates what we've just done. So we said that our horizontal velocity, or our vertical velocity, we're going negative 35.4 meters per second downwards. And we also said that our final velocity in the x direction, well, that's 23, that's going to be 23.0 meters per second, to the right, right? Because we're dealing with in the x direction. So our net velocity is going to be equal to, well, it's going to be equal to this velocity vector right over here that I've drawn. Remember when we had our velocity vector, something like this, and we split it up into x components and y components of that velocity? Well, this is just kind of like undoing that. We're given the x component and the y component, and then we want to solve for our original component, right? And in order to do that, well, you probably guessed right, we just have to do a Pythagorean theorem, right? So I have to make this a little bit more clear, but our y velocity, it's going to be negative 35.4 downwards, and then x velocity is going to be 23 meters per second to the right. So all we have to do is solve for the length of this hypotenuse as well as the direction, or you can say this angle right over here. We also have to solve for this angle, right? Because initially, you can see how the projectile was launched from the top of a cliff at blah, 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 at 40 degrees. So it gives you the angle at which it was launched, right? 40 degrees. So in this final problem, it also wants us to find the angle relative to, the horizontal, or relative to the ground, right? So how do we do this? Well, first one, we can just do Pythagorean theorem. So we can do a squared plus b squared is equal to c squared, which we're going to call this side right over here. And then when we actually compute all of this stuff, we get around 42.2. We get around 42.2 meters per second. So that's going to be this right over here. I don't know why that deleted, but okay, so this is going to be 42.2. But we're not done yet, because remember, velocity has a magnitude. We found the magnitude, but it also has this direction. And with this angle right over here is going to be equal to negative 35.4 divided by 23. So if I take inverse tan of both sides, well, then this cancels out, and I get that the angle relative to the ground is going to be equal to approximately 57 degrees. So that means this angle right over here is 57 degrees. So that means that my final answer is going to be like, where we're going to be traveling at a velocity of 42.21 meters per second, and my direction is going to be like 57.0 degrees, sort of below the horizontal.